Out there in the silent depths of space, hidden among the stars, are objects so strange and powerful they defy everything we know about physics. Imagine a star so dense that a single teaspoon of its material would weigh as much as a mountain, more than Mount Everest crushed down into something the size of a sugar cube. That's the mind-bending reality of neutron stars, the universe's ultimate cosmic pressure cookers. And if that wasn't bizarre enough, some of them spin faster than a kitchen blender, sending out beams of radiation so precise they pulse like cosmic lighthouses, earning them the name pulsars. These aren't just curiosities, they're extreme laboratories where matter gets pushed to its absolute limits, where gravity warps space-time into knots, and where the laws of physics as we know them start to break down. What makes these objects even more fascinating is how little we truly understand about them. Neutron stars and pulsars are packed with mysteries, from how they are born in the violent deaths of massive stars to the strange quantum soups swirling inside them. Some pulse with eerie, almost musical radio waves that sound like ghostly heartbeats when converted into sound. Others unleash bursts of energy so powerful they can be detected clear across the galaxy. And then there are the Magnetars, neutron stars with magnetic fields so intense they could rip apart atoms from thousands of miles away. These cosmic oddities challenge our very understanding of reality, and yet they're out there right now, spinning, pulsing, and hiding secrets just waiting to be uncovered. That's exactly what we're diving into today. 25 of the most incredible, head-scratching, and downright shocking mysteries surrounding neutron stars and pulsars. We'll explore how they form in supernova explosions so violent they outshine entire galaxies, what happens to matter when it's crushed beyond recognition, and why some of these stars suddenly speed up without warning. We'll even take a peek at the hypothetical quark stars, objects so extreme they might make neutron stars look tame by comparison. Whether you're a seasoned space enthusiast or just someone who loves a good cosmic mystery, this journey will take you to the very edge of what's possible in our universe. So buckle up, we're about to venture into one of the most extreme corners of space where the rules as we know them don't just bend, they shatter. The universe has a way of turning endings into beginnings, and nowhere is that more violent or awe-inspiring than in the birth of a neutron star. Picture a massive star, one at least 8 times heavier than our Sun, burning through its fuel over millions of years. When it finally runs out, the delicate balance between gravity pulling inward and nuclear reactions pushing outward shatters. In less than a second, the star's core collapses under its own weight, triggering a supernova explosion so bright it can outshine an entire galaxy. But the real magic happens in the wreckage. As the outer layers blast into space, the core, now free from the crushing pressure of fusion, implodes with unimaginable force. What's left is something straight out of science fiction, a neutron star. In that split second of collapse, protons and electrons are squeezed together so tightly they merge into neutrons, forming a sphere no bigger than a city but packing more mass than our Sun. To put that density into perspective, if you could scoop up just a sugar cube's worth of this material, it would weigh 1 billion tons on Earth. Yet for all we know about this process, there are still glaring mysteries. Not every dying massive star leaves behind a neutron star. Some vanish without a trace, while others collapse into black holes under circumstances we don't fully understand. Even more puzzling is why neutron stars emerge with such wildly different magnetic fields. Some are relatively tame, while others, the Magnetars, wield forces so strong they could strip the data off a credit card from halfway across the Milky Way. The chaos of a supernova should, in theory, leave neutron stars spinning wildly, yet many rotate surprisingly slowly. Others, like the famous crab pulsar, whip around dozens of times per second. Why the inconsistency, and what determines whether a dying star's core becomes a neutron star or something even stranger? These aren't just academic questions, they're clues to the fundamental laws governing matter under the most extreme conditions the universe can conjure. Every neutron star is a fossil from a star's explosive death, and by studying them, we're piecing together the final moments of these cosmic giants, one mystery at a time. If you think a kitchen blender spins fast at a few hundred rotations per minute, neutron stars will make your head spin, literally. Some of these cosmic remnants whip around at dizzying speeds, completing an entire rotation in just a fraction of a second. The current record holder, known as PSRJ1 748-2446 AD, spins an astonishing 700 times every second. That's faster than the blades of a jet engine, packing the mass of our Sun into a sphere no wider than Manhattan and spinning it at nearly a quarter the speed of light. How does something so dense and massive end up rotating like a cosmic top? The answer lies in one of physics' most fundamental laws, the conservation of angular momentum. Picture an ice skater pulling their arms in during a spin, causing their rotation to speed up dramatically. Now imagine that skater is a massive star collapsing under its own gravity, shrinking from millions of miles across to just 12 miles in diameter. All that rotational energy from the star's original, slower spin gets concentrated into an object exponentially smaller, launching the newborn neutron star into a frenzied whirl. But here's where things get even stranger. While most neutron stars slow down gradually as they blast energy into space, some do the opposite. They suddenly speed up in unpredictable bursts called glitches. These aren't minor hiccups. Some pulsars have been caught gaining hundreds of extra rotations per second in a matter of minutes, as if an invisible hand gave them a violent push. The leading theory behind these glitches involves quantum weirdness deep inside the neutron star. Beneath the solid crust, the core is thought to be a superfluid, a bizarre state of matter that flows without friction, where atoms sync up and move as one. When the outer crust slows down due to magnetic drag, this inner superfluid might lag behind, storing energy like a wound-up spring. Eventually, the tension becomes too much, and the superfluid's vortices, tiny whirlpools of quantum fluid, suddenly transfer their pent-up momentum to the crust, kicking the star's rotation into overdrive. Yet, even this explanation leaves gaps. Why do some pulsars glitch repeatedly while others never do? What triggers the exact moment of a speed burst? And could there be an even stranger layer of physics at play, like exotic particles or undiscovered forces lurking in that hyper-dense core? Each glitch is a cosmic telegram from the heart of a neutron star, and decoding its message might rewrite our understanding of matter itself. Beneath the scorched, crystalline crust of a neutron star lies a realm where matter stops behaving like anything we recognize. Forget solids, liquids, or even plasma. This is a place where atomic nuclei are crushed so tightly they dissolve into a seething ocean of neutrons, packed shoulder to shoulder like commuters in a cosmic subway. But go deeper and things get even weirder. At these unimaginable pressures, millions of times greater than Earth's core, physicists suspect neutrons themselves might shatter into their fundamental building blocks, a swirling soup of quarks and gluons. This quark-gluon plasma isn't just hypothetical. For fleeting moments in particle colliders on Earth, we've recreated conditions hot and dense enough to break protons and neutrons apart into this primordial state. The same stuff thought to have filled the universe microseconds after the Big Bang. Yet inside a neutron star, this plasma could be frozen into bizarre new phases by the crushing gravity. Some theories suggest quarks might pair up into superconducting duos flowing without resistance, while others predict an even stranger possibility: strange matter. Made of strange quarks, an exotic, heavy cousin to the usual up and down quarks, this material could be the ultimate stable form of matter in the universe. If it exists, a single speck might convert anything it touches into more strange matter, rewriting the very fabric of reality. But how do we study something buried under 12 miles of impenetrable neutronium? The answer comes from ripples in spacetime itself. When neutron stars collide, a cataclysm so violent it bends the fabric of the universe, the resulting gravitational waves carry fingerprints of their internal structure. Instruments like LIGO and Virgo detect these tremors, allowing scientists to hear how stiff or squishy neutron star matter behaves under extreme strain. A softer interior would suggest free-flowing quark soup, while a stiffer one hints at intact neutrons holding their ground, yet the data so far leaves room for debate. Some collisions match predictions for quark cores, while others defy expectations entirely. Perhaps the greatest enigma is this: neutron stars might not be uniform inside at all. Layers could exist like the strata of an alien onion, a brittle crust of iron noodles, a mantle of neutron-rich Pulsar phases, and a core where the rules of quantum physics blur into something beyond our theories. Until we can peer deeper, or until a nearby neutron star does something truly inexplicable, these ultra-dense cosmic puzzles will keep challenging our understanding of what matter can become when pushed to the absolute edge of existence. If you've ever stood on a rocky shore watching the rhythmic flash of a lighthouse cutting through the dark, you've witnessed something eerily similar to one of the universe's most precise timekeepers, the pulsar. These spinning neutron stars don't just emit radiation, they funnel it into narrow beams that sweep across space like cosmic searchlights, blinking with a regularity so precise it rivals atomic clocks. But while earthly lighthouses shine predictably, pulsars sometimes throw astronomers for a loop. Their pulses can flicker, dim without warning, or even vanish entirely, as if someone flipped a switch in the depths of space. Take the case of the Black Widow pulsar, a celestial predator with a taste for destruction. This pulsar isn't alone. It orbits a smaller companion star, locked in a gravitational dance with deadly consequences. With each pass, the pulsar's intense radiation and particle winds strip away layers of its partner, slowly vaporizing it into a glowing trail of stellar debris. The process is so violent that astronomers named it after the spider that devours its mate. Yet even in this cosmic drama, the pulsar's beams behave mysteriously. Some pulses arrive brighter than others, and occasionally the entire signal winks out for minutes or even hours before returning as if nothing happened. What could cause such erratic behavior? One theory points to the pulsar's magnetosphere, the turbulent zone of charged particles trapped by its magnetic field. If this region becomes unstable, it might distort or even block the beams from our line of sight. Another idea suggests that material stolen from the companion star could form dense clouds around the pulsar, acting like cosmic blinds that intermittently obscure its light. But the strangest possibility involves the beams themselves. Unlike the steady glow of a lighthouse bulb, pulsar radiation is generated by particles accelerating along magnetic field lines near the star's poles. If those lines twist or reconfigure, perhaps due to quakes in the neutron star's crust, the beams could falter or shift direction entirely. Then there's the enigma of nulling pulsars, which don't just dim but go completely silent for stretches of time. Some switch off for days or months before roaring back to life, defying all predictions. Is this the pulsar equivalent of a battery dying, or is something more profound at work? Could it be that under certain conditions, the engine driving these beams, a dynamo of spinning magnetic fields, simply stalls? Every flicker, every silence is a clue waiting to be deciphered, a whisper from a realm where matter is so dense it twists the very rules of physics. And as we listen to these cosmic lighthouses, their mysteries only deepen, reminding us that even the most clockwork phenomena in the universe hide secrets beneath their surface. In February 1987, astronomers witnessed something extraordinary, a star exploding in our cosmic backyard. supernova 1987A, located just 168,000 light-years away in the Large Magellanic Cloud, became the closest observed supernova in modern history. For months, it blazed brighter than 100 million suns, offering front-row seats to the death of a massive star. Decades later, scientists are still baffled by one glaring omission: where's the pulsar? When a star that size collapses, physics demands one of two outcomes. Either it forms a neutron star, rapidly spinning and pulsing with radiation, or it crushes itself into a black hole. Yet despite exhaustive searches across radio, X-ray, and gamma-ray wavelengths, no pulsar has ever been detected in the wreckage of 1987A. It's like finding the smoldering remains of a fireworks factory, but no trace of the explosion's trigger. What could have happened to this stellar corpse? One possibility is that we're simply not looking at the right angle. Pulsars beam radiation in narrow cones from their magnetic poles. If those beams don't happen to sweep across Earth, the star remains invisible to our telescopes. It's like trying to spot a disco ball in a dark room while standing directly under it. Unless the rotating mirrors catch the light just right, the effect is lost. But after nearly 40 years of monitoring, the odds of a misaligned beam seem slim. Then there's the darker alternative: what if the collapse didn't stop at a neutron star? Simulations suggest that in some supernova, debris can rain back onto the newborn core with such force that it tips the scales past neutron star density, forming a black hole. This fallback scenario might explain the silence, yet even this theory has wrinkles. Fallback collapses are thought to happen within days or weeks, but some observations hint at lingering activity in the remnant glows that could suggest a hidden neutron star shrouded by dust. Perhaps the most tantalizing clue comes from recent neutrino detections. Just hours before 1987A's light reached Earth, underground sensors picked up a burst of these ghostly particles, exactly what you'd expect from a neutron star's birth. If one formed that day, where is it now? The answer might lie buried under a thick blanket of stellar debris, its light absorbed by expanding gas clouds. Or maybe, in a twist no one predicted, this particular stellar corpse is something stranger: a quark star, a magnetar in hibernation, or an object we haven't even imagined yet. Until we peer deeper into the heart of that explosion, 1987A's missing pulsar remains one of modern astronomy's most stubborn puzzles. At the heart of every neutron star lies a cosmic tightrope walk, a delicate balancing act between the crushing force of gravity and the quantum resistance of matter pushed beyond its limits. Physics tells us there's a point where even the sturdiest neutron star should buckle, collapsing into a black hole. This breaking point, known as the Tolman-Oppenheimer-Volkoff limit, was long thought to cap neutron stars at around 2.2 times the mass of our Sun. But the universe loves a curveball. Recent discoveries have revealed neutron stars tipping the scales at nearly 2.5 solar masses, dangling precariously over the theoretical edge without slipping into oblivion. How do these cosmic heavyweights defy gravity's ultimate verdict? One clue comes from their dizzying spins. Like a roller coaster rider pinned to their seat by centrifugal force, a rapidly rotating neutron star can use its own motion to stave off collapse. The faster it whirls, the more its outer layers are flung outward, counteracting gravity's inward pull. This might explain stars like PSR J0348 plus 0432, a pulsar spinning over 400 times per second while packing twice the Sun's mass into a sphere smaller than Boston. But rotation alone can't account for every heavyweight contender. Some oddly massive neutron stars, like the one discovered in the binary system J0740 plus 6620, rotate relatively slowly yet still flirt with the theoretical limit. That's where the real enigma begins. Beneath their crusts, these stars might harbor something even stranger than pure neutron matter, exotic particles or phases of matter we've never observed on Earth. Quantum chromodynamics, the theory governing quarks and their interactions, suggests that under such extreme pressures, neutrons might dissolve into a free-floating quark soup. If certain quarks inside this brew, particularly the elusive, strange quark, form stable configurations, they could generate additional outward pressure, propping up the star against collapse. There's even speculation about hypothetical particles like hyperons, which contain strange quarks and could emerge under these insane densities, acting like microscopic scaffolding to reinforce the star's core. Yet the plot thickens when we look at neutron stars born from collisions. In 2017, gravitational wave observatories detected two neutron stars merging, an event dubbed GW 170817. The resulting object initially appeared to be the heaviest neutron star ever observed, briefly surpassing 2.7 solar masses before vanishing from telescopes. Did it immediately collapse into a black hole, or did it cling to existence for a few fleeting seconds as an unstable, ultra-dense hybrid? The answer could rewrite our understanding of the TOV limit itself. Perhaps the most tantalizing possibility is that we've underestimated nature's ingenuity altogether. Some theorists argue that the true upper mass limit isn't a fixed number but a spectrum, influenced by factors we're only beginning to grasp. The star's internal temperature, magnetic field geometry, or even the presence of dark matter. Others propose that certain neutron stars might briefly cross the threshold into black hole territory, only to rebound thanks to quantum effects or phase transitions in their cores. Every time we think we've found the ultimate boundary, another cosmic outlier emerges, laughing in the face of our equations. These gravitational rebels aren't just oddities, they're stress-testing the very foundations of particle physics, daring us to rethink what's possible when matter is pushed to the brink. Imagine a magnetic field so strong it could erase every hard drive on Earth from halfway to the Moon. That's the terrifying power of a magnetar, a neutron star that dials its magnetic field up to 11, reaching strengths a quadrillion times greater than our planet's. These cosmic monsters don't just bend the rules of physics, they shatter them, generating forces so intense they twist the very fabric of space-time around them. But here's the puzzle. If all neutron stars are born from the same violent stellar collapses, why do only a fraction of them become these magnetic extremists? The secret might lie in the chaos of their birth. When a massive star goes supernova, its spinning core doesn't just collapse, it convulses with turbulent flows of plasma acting like a dynamo on steroids. Under just the right conditions, this swirling inferno can amplify the star's magnetic field exponentially, imprinting it into the newly formed neutron star like a cosmic fingerprint. But the process is fickle. Some theorists argue it requires a perfect storm, a rapidly rotating progenitor star with a specific internal structure, or perhaps a delayed collapse that allows magnetic fields to build longer than usual. Others suggest magnetars might emerge from binary systems where stellar interactions before the supernova spin up the core like a top, yet the real drama begins after formation. Magnetars don't just sit there, they crack under pressure. Literally, their crusts, already under unimaginable strain, occasionally rupture in violent starquakes, releasing pent-up energy in gamma-ray flares bright enough to outshine entire galaxies for seconds at a time. The most powerful of these eruptions, like the one detected from SGR 1806-20 in 2004, briefly disrupted Earth's ionosphere from 50,000 light-years away. That's equivalent to feeling the heat of a candle on the Moon. What's even stranger is how these magnetic behemoths fade. Over millennia, magnetars appear to lose their ferocious fields, gradually calming into ordinary neutron stars. Current theories suggest their fields might slowly dissipate through a quantum process called ambipolar diffusion, where charged particles leak energy into the star's core. But there are outliers, magnetars like XTJ 1710-378, which still pulses with youthful intensity despite being an estimated 40,000 years old. Could some hidden mechanism be recharging their magnetic batteries, or are we witnessing the death throes of fields that once burned even brighter? Every magnetar flare, every ripple in their crusts is a message from the edge of physical possibility, a reminder that even in the cold depths of space, magnetism can reach levels so extreme they border on the supernatural. Every cosmic clock winds down, eventually even the precise, rapid ticks of a pulsar. Over thousands of years, these spinning neutron stars gradually lose steam, their rotation slowing as they bleed energy into space. It's a phenomenon called spin down, and at first glance the culprit seems obvious: magnetic braking. Picture a pulsar as a colossal lighthouse with its beams locked into the star's magnetic field. As those beams sweep through space, they carry away angular momentum, acting like invisible brakes that sap the star's spin. The stronger the magnetic field, the quicker the slowdown, which is why magnetars, with their off-the-charts magnetism, grind to a crawl in mere millennia, while gentler pulsars keep spinning for millions of years. But then there's the Vela pulsar, a cosmic rebel that doesn't just slow down, it stutters. Unlike the smooth deceleration of most pulsars, Vela occasionally slams on the brakes, losing chunks of rotational speed in sudden, jarring events known as glitches in reverse. These anti-glitches are rare, unpredictable, and utterly perplexing. If a regular glitch is like a car lurching forward when the gas pedal sticks, Vela's slowdowns are the equivalent of hitting an invisible speed bump mid-cruise. So what's jolting this pulsar off its rhythm? One explanation lies beneath the star's ironclad surface. Deep inside a neutron star, the core isn't just a static clump of neutrons. It's thought to be a superfluid, a frictionless quantum liquid where particles move in perfect lockstep. Normally, this superfluid rotates slightly faster than the crust, storing energy like a wound-up spring. But when the crust slows due to magnetic braking, the superfluid's vortices, tiny whirlpools in this quantum soup, can suddenly transfer momentum outward, causing a speed-up, a glitch. However, in rare cases, something far stranger might happen. The vortices could tangle or pin to the crust's crystalline structure, effectively anchoring parts of the superfluid. When these pinned vortices release, they might drag the crust's rotation down with them instead of propping it up, resulting in an abrupt slowdown. Then there's the starquake theory. Neutron stars aren't perfectly smooth spheres. Their crusts are under unimaginable tension, squeezed by gravity and torqued by magnetic fields. Occasionally, this strain becomes too much and the crust fractures like a frozen lake cracking under pressure. These starquakes can abruptly change the star's shape, altering its moment of inertia, essentially redistributing its mass like a figure skater extending their arms mid-spin. If the quake shifts mass outward, the pulsar slows down suddenly, mimicking Vela's behavior. There's even evidence that some of these quakes might be linked to magnetar-like activity, where magnetic fields twist the crust until it snaps, releasing pent-up energy in a way that affects the star's spin. But here's the kicker: sometimes the slowdowns precede observable starquakes, as if the star's interior is sending distress signals before the crust finally gives way. It's as if the pulsar is whispering secrets about its internal structure through these tiny rotational hiccups, offering clues to the chaotic interplay between quantum mechanics and gravity. The Vela pulsar, with its erratic behavior, is more than just an outlier. It's a Rosetta Stone for understanding how neutron stars age, how their insides churn, and ultimately, how even the most precise clocks in the universe can't escape the chaos lurking beneath their surfaces. If neutron stars are supposed to be the universe's most common stellar corpses, then where are they all hiding? Astronomers have stumbled upon a cosmic detective story, a glaring mismatch between the number of neutron stars we should see and the ones we actually detect. Take the heart of our galaxy, the Milky Way. This dense, star-packed region should be littered with the remnants of dead massive stars, their neutron cores spinning quietly in the dark. Yet when we point our telescopes toward the galactic center, we find almost nothing. It's like walking into a graveyard and discovering half the tombstones are missing. One explanation is simple: camouflage. The Milky Way's core is a swirling storm of gas and dust, thick enough to blot out visible light entirely. Neutron stars, especially older ones that have cooled and stopped pulsing, might be lurking unseen behind these cosmic curtains, their faint X-ray whispers muffled by interstellar debris. There's precedent for this. Some neutron stars, like the enigmatic Calvera, were only discovered because they occasionally pierce through the fog with brief X-ray flares. But even accounting for obscuration, the numbers still don't add up. Statistically, we should be tripping over neutron stars in this region, yet they remain stubbornly absent. That leads to a far more dramatic possibility. What if these stars didn't just fade into the background? What if they ran away? When a supernova explosion isn't perfectly symmetrical, the newborn neutron star can get a staggering kick, rocketing through space at speeds exceeding 1,000 kilometers per second. We've actually caught a few of these stellar fugitives in the act, like the cosmic cannonball, a pulsar racing away from the galactic plane fast enough to escape the Milky Way entirely. If this happens routinely, it could explain why the galactic center seems so empty. Neutron stars born there might have been violently ejected, leaving behind ghostly trails in their wake. But there's an even stranger twist. Some theorists argue that the dark neutron star problem hints at an entirely new class of objects, neutron stars so cold and inactive they've slipped below our detection thresholds. Imagine a stellar corpse that's exhausted all its thermal energy, no longer pulsing, no longer glowing in X-rays, just a pitch-black sphere drifting silently through space. These black neutron stars would be nearly impossible to spot unless they passed directly in front of a distant star, bending its light with their gravity. Or worse, what if some of them did collapse into black holes, but so quietly we never noticed? The mystery deepens when we look beyond our galaxy. In star-forming regions like the Large Magellanic Cloud, where massive stars live fast and die young, neutron stars do appear in expected numbers. Why the discrepancy? Could the Milky Way's central black hole, Sagittarius, a star, be disturbing the normal processes of stellar death, either by ripping apart progenitor stars before they can collapse or flinging neutron stars away with its gravity? Every missing neutron star is a silent challenge to our assumptions, forcing us to question whether we truly understand how these objects are born, how they evolve, and what they become when the lights finally go out. Until we solve this cosmic game of hide and seek, the galaxy's darkest corners will keep their secrets. Some of the most violent cosmic relationships in the universe unfold in X-ray binary systems, where a neutron star and its stellar partner are locked in a deadly gravitational tango. Unlike solitary pulsars spinning quietly in the dark, these neutron stars have a voracious appetite, slowly devouring their companion star piece by piece. As material gets torn away by the neutron star's immense gravity, it doesn't just fall straight in. Instead, it spirals into a superheated accretion disk, a whirlpool of plasma so energetic it blasts out X-rays visible across galaxies. These systems aren't just cosmic oddities, they're extreme laboratories where matter is pushed to its limits and where space-time itself warps under the strain. Take the infamous Scorpius X1, one of the brightest X-ray sources in our sky. Here, a neutron star no bigger than Manhattan orbits so close to its companion that it sucks away stellar material at a staggering rate, about 1 Earth mass every year. As this gas funnels onto the neutron star's surface, temperatures soar to hundreds of millions of degrees, triggering thermonuclear explosions called Type I X-ray bursts. These flashes can outshine our sun 100,000 times over in mere seconds. Yet what's truly baffling is how erratic these outbursts can be. Some systems flare like clockwork, while others, like the enigmatic rapid burster, alternate between predictable eruptions and utterly chaotic ones, as if flickering between two separate modes of cosmic cannibalism. The key to this unpredictability might lie in the accretion disk's turbulent dynamics. Picture a faucet turned on just enough that water drips sporadically instead of flowing smoothly. Similarly, in some X-ray binaries, gas might pile up in the disk until it reaches a critical threshold, then cascade onto the neutron star all at once. But other factors like the companion star's magnetic field or the neutron star's rotation could disrupt this flow, creating wild variations in feeding patterns. Even more bizarre are the heartbeat systems, where the disk flickers with rhythmic pulses, expanding and contracting like the chambers of a cosmic heart, driven by feedback loops between radiation pressure and gravity. But the real spectacle happens when Einstein's theories take center stage. In extreme cases like the Black Widow pulsar PSRB 1957+20, the neutron star doesn't just siphon gas, it vaporizes its companion with relentless particle winds, carving it into a glowing comet-like tail. The sheer energy involved distorts spacetime around the system, creating measurable delays in the pulsar's signal as light struggles to climb out of this gravitational well. Some systems, like the recently discovered Swift J1-858.6-0814, even exhibit quasi-periodic oscillations, faint X-ray flickers thought to be caused by clumps of material scraping against the very edge of the neutron star's event horizon, where time itself slows to a crawl. What makes these cosmic feeding frenzies even more mysterious is how they might end. Given enough time, some neutron stars will completely consume their partners, leaving behind a lone pulsar. Others might destabilize their orbits and fling their companions away entirely, like a diner tossing aside an empty plate. But a rare few could face an even darker fate. If the neutron star gorges itself past a critical mass, it might collapse into a black hole mid-meal, vanishing from the X-ray sky without warning. Every flicker, every burst from these systems is a clue to the chaotic physics of extreme gravity, a reminder that even in the void of space, hunger can reshape the fabric of reality itself. In the vast silence of space, some neutron stars don't just whisper, they scream. Fast radio bursts, or FRBs, are among the universe's most enigmatic signals, blasts of radio waves so intense they can outshine entire galaxies for mere milliseconds. The sheer power behind these cosmic flashes is staggering, releasing as much energy in 1,000th of a second as our Sun does in 3 days. And while we've traced some of these outbursts back to magnetars, the most magnetic monsters in the cosmos, the story doesn't end there. Because not all FRBs play by the same rules. Some fire once and vanish without a trace, while others repeat like clockwork, pulsing from regions of space where no magnetar should exist. Take the case of the first repeating FRB ever discovered, known as FRB 121102. Unlike one-off bursts tied to catastrophic magnetar flares, this source has been spitting out radio screams sporadically since 2015, with no pattern to its eruptions. Stranger still, it lives in a dwarf galaxy teeming with young stars, an environment completely unlike the chaotic neighborhoods of magnetars. If these bursts truly came from neutron stars, why do some behave like unruly children throwing tantrums while others stay silent for years? One clue emerged in April 2020 when a magnetar in our own galaxy, SGR 1935+2154, erupted with a radio blast eerily similar to an FRB. For the first time, we had proof that at least some of these signals could be tied to neutron stars, but the magnetar's burst was thousands of times weaker than typical FRBs, like comparing a firecracker to a nuclear bomb. This raises a haunting question: what could supercharge a magnetar's flare to such extreme levels? Some theorists suggest it might involve a starquake tsunami, where the neutron star's crust fractures in a cascading collapse, releasing pent-up magnetic energy all at once. Others propose that interactions with debris from a past supernova, or even an unseen companion star could amplify the outburst. Then there's the puzzle of the non-repeaters. If Magnetars explain the one-off FRBs, why haven't we detected any more from the same locations? One possibility is that these bursts stem from neutron star mergers, collisions so violent they tear spacetime apart, producing gravitational waves alongside a final, desperate radio scream. Yet even this theory falters when faced with FRBs like the one detected from a quiet, elderly galaxy in 2022, a place where stellar collisions are vanishingly rare. Could there be an entirely new class of neutron stars lurking in these calm cosmic backwaters, ones that generate radio bursts through mechanisms we haven't even imagined? The most tantalizing and unsettling explanation is that we're seeing the fingerprints of physics beyond our current understanding. Some models suggest FRBs might emerge from action stars, hypothetical blobs of dark matter that could collapse near neutron stars, releasing energy in bizarre, concentrated pulses. Others speculate about Pulsars, neutron stars so massive they're on the verge of collapsing into black holes, their magnetic fields snapping like rubber bands as they cross the threshold. With every new detection, the mystery deepens, pulling us further into a cosmic whodunit where the usual suspects Magnetars, mergers, even black holes keep finding holes in their alibis. Until we catch one of these radio screamers in the act mid-eruption, their origins will remain one of neutron star astronomy's most electrifying unsolved cases. Not all neutron stars announce themselves with brilliant beams or violent stellar feasts. Some drift through the cosmos like ghost ships, silent and undetected. These isolated neutron stars, stripped of pulsar activity and companion stars, might be the most elusive stellar remnants of all. Unlike their flashy cousins, they don't pulse with radio waves or devour neighboring gas. Instead, they emit only faint X-rays, the last whispers of heat left over from their cataclysmic births billions of years ago. The mystery: if neutron stars are born spinning and magnetized, why do so many end up as dark, solitary wanderers? Take the Magnificent Seven, a group of nearby isolated neutron stars that defy expectations. Named for their rarity and faint glow, these objects are so cold they barely register above the cosmic background, some with surface temperatures below 1 million degrees, colder than many laboratory-produced plasmas on Earth. They shouldn't even be detectable, yet there they are, drifting through space without beams, without companions, and without any obvious source of energy to explain their feeble X-ray glow. One leading theory suggests they're the elderly survivors of a once vibrant pulsar population, their magnetic fields having decayed over eons until they could no longer power brilliant beams. But that doesn't quite explain why some, like the dim X-ray source RxJ1 856.5-3754, still flicker with occasional bursts of energy, as if something inside them refuses to die quietly. Then there's the puzzle of their birth. Some isolated neutron stars might have been born alone, their progenitor stars flinging them away during asymmetric supernova. Others could have started in binary systems, only to be divorced by a partner's explosive death or a gravitational kick strong enough to send them careening into the void. But the strangest possibility is that these objects never pulsed at all. A subset of neutron stars might form with unusually weak magnetic fields from the start, skipping the pulsar phase entirely and cooling into obscurity faster than their magnetized siblings. The Magnificent Seven add another layer of intrigue. Unlike typical neutron stars, some of these objects exhibit absorption features in their X-ray spectra, dips in their glow that hint at exotic surface chemistry or ultra-strong magnetic fields trapped just beneath their crusts. Could these be signs of hyperon stars, where exotic particles seep to the surface, or evidence of quantum condensates forming in the star's frigid outer layers? Even their motion tells a story. One member of the group, RxJ0 806.4-4123, streaks through space at an unusual angle, suggesting it might have been born in a globular cluster before being ejected into the galactic wilderness. The most haunting question remains: how many more of these ghosts are out there, invisible to our telescopes? Current estimates suggest the Milky Way could harbor hundreds of millions of neutron stars, yet we've detected only a tiny fraction. The rest might be lurking in the dark, their faint heat swallowed by interstellar dust or their signals too weak to distinguish from cosmic noise. If we could listen closely enough, the silent symphony of these isolated wanderers might rewrite our understanding of stellar death, proving that even in the quietest corners of the universe, neutron stars still have secrets to spill. Most cosmic objects slow down predictably over time, but neutron stars love to defy expectations. While most pulsars gradually lose speed as they radiate energy into space, a handful do the exact opposite. Instead of spinning faster in sudden glitches, they slam on the brakes without warning, an event so counterintuitive physicists call it an anti-glitch. Imagine a figure skater spinning smoothly, arms tucked in, when suddenly, for no apparent reason, they fling their arms outward, slowing their rotation mid-spin. That's the baffling behavior of stars like 1 ESO 0075-7155, a magnetar that lost significant speed in just hours, as if an invisible hand reached out and grabbed it. What could trigger such a violent slowdown? One leading theory points to the star's magnetic field, a tangled web of forces so intense it warps the neutron star's very structure. If these fields suddenly reorganize, snapping into a new configuration like a rubber band pulled too tight, the energy release could literally drag on the star's rotation. Picture a spinning top wrapped in elastic bands. If those bands suddenly tighten, the top would jerk slower. Magnetars, with their off-the-charts magnetic fields, might be especially prone to these abrupt reconfigurations, explaining why anti-glitches seem concentrated among them. Then there's the starquake scenario. Neutron star crusts aren't smooth shells, they're fractured landscapes under unimaginable strain, squeezed by gravity and torqued by magnetic fields. Occasionally, these crustal plates might shift like tectonic slabs, causing the entire star to stumble in its spin. A recent observation of the magnetar 1E1841-0456 adds weight to this idea. Its anti-glitch coincided with an X-ray burst, as if the crust cracked and settled into a new position. The catch: some anti-glitches precede detectable starquakes, suggesting the real action happens deep inside, where the crust meets the quantum chaos of the core. Perhaps the strangest explanation involves the neutron star's superfluid interior. Beneath the solid crust, neutrons might flow without friction, spinning independently like a whirlpool inside a bucket. Normally, this superfluid transfers momentum to the crust, causing glitches. But if vortices in this quantum soup suddenly latch onto crustal imperfections, think of a spinning carousel with brakes sporadically grabbing its poles. They could transfer momentum away instead, yanking the star's rotation down. The Vela pulsar's bizarre slowdown in 2016 fits this eerie pattern, behaving as though its internal engine briefly ran in reverse. Yet every new detection deepens the puzzle. Why do some neutron stars experience both glitches and anti-glitches, while others stick to one script? Could anti-glitches be a hidden phase in every pulsar's life, emerging only when conditions align? Or are we witnessing the birth pangs of an entirely new class of neutron stars, ones where the rules of spin don't just bend but invert? Until we catch one of these cosmic breaks in the act, mid-slowdown, these backward stumbles will remain one of the most tantalizing quirks in the neutron star playbook. Among the strangest survivors in the cosmos are the planets that shouldn't exist, worlds orbiting pulsars, the stellar zombies left behind after supernova explosions. These aren't the gentle, life-nurturing exoplanets we often imagine. They're battered relics dancing in the graveyard of a dead star's fury. The first of these pulsar planets ever discovered, PSRB 1257+12, defies all expectations. Instead of a gas giant or a rocky world like Earth, this system hosts what might be the universe's most extravagant gemstone, a planet likely made of crystallized carbon, essentially a cosmic diamond the size of a star. How could anything endure the apocalypse that births a neutron star? When a massive star goes supernova, the explosion unleashes enough energy to vaporize nearby planets 10 times over. Yet here they are, worlds like PSRB 1257+12's 3 oddball companions locked in orbit around a rapidly spinning corpse. One theory suggests these planets might be the charred remains of gas giants, their outer layers blasted away until only their ultra-dense cores remained. Another possibility is even wilder. They could be second-generation worlds, born after the supernova from a disk of debris that somehow reformed around the pulsar. The diamond planet scenario isn't just poetic speculation. Under the extreme pressures near a pulsar, carbon-rich material could compress into crystalline structures akin to terrestrial diamonds, but on a planetary scale. Meanwhile, other pulsar planets, like those orbiting PSRJ 1719-1438, might be the shattered fragments of a binary companion star, torn apart by the neutron star's gravity and reassembled into new Frankenstein-like worlds. But the real enigma isn't just their survival, it's their detection. Pulsars, with their clockwork radio pulses, offer one of the most precise ways to spot orbiting bodies. Tiny wobbles in the pulsar's signal, caused by gravitational tugs from unseen planets, betray their presence. Some of these worlds orbit so close that a year lasts mere Earth days, skating perilously close to the neutron star's lethal radiation. Others, like the mysterious outlier in the PSRJ 031, 4+0613 system, follow elongated, comet-like paths that suggest a violent past of gravitational scattering. The most haunting question remains: could these hostile worlds teach us about planet formation in the most extreme environments? If planets can coalesce from the ashes of a supernova, or outlast a star's death throes, what does that say about the resilience of cosmic material? Every pulsar planet is a rebuke to our assumptions, a reminder that even in the universe's most violent neighborhoods, the seeds of new worlds find a way. When a neutron star unleashes an X-ray burst, the blast is so intense it can momentarily outshine entire galaxies. But sometimes, astronomers catch something unexpected: faint, ghostly echoes trailing the main burst like ripples in a cosmic pond. These delayed signals, arriving seconds or even minutes after the initial flash, aren't just random noise. They're clues to one of the most perplexing neutron star mysteries: what's bending light and time around these objects to create these eerie afterimages. One possibility is as mind-bending as it sounds. The echoes might be literal reflections of space-time itself, warping under the neutron star's immense gravity. Einstein's theory of general relativity predicts that massive objects dent the fabric of the universe, causing light to follow curved paths. Around a neutron star, where gravity is second only to a black hole's, radiation from a burst could get trapped in orbital loops before finally escaping to our telescopes. Picture a flashlight beam in a hall of mirrors. Some photons take the direct route to us, while others get delayed as they spiral through this gravitational funhouse. The time gap between the main burst and its echoes would then act like a cosmic stopwatch, measuring just how severely the neutron star twists the space around it. Yet there's another contender: cosmic dust. Neutron stars, especially those born from recent supernova, often sit amid clouds of debris. When an X-ray blast slams into these dust grains, some radiation scatters in random directions, like sunlight bouncing off fog. This could create delayed light echoes as photons take detours through the nebula before reaching us. In 2022, observations of the neutron star SXTE-J1810-197 hinted at this when its X-ray bursts were followed by faint rings of emission, expanding outward like shockwaves in slow motion, a smoking gun for dust scattering. The real intrigue lies in distinguishing between these two explanations. Gravitational echoes would provide a rare test of general relativity in extreme conditions, potentially revealing deviations from Einstein's predictions. Dust echoes, meanwhile, could map the hidden structures around neutron stars, showing us where supernova debris is concentrated. Some bursts, like those from the Magnetar 1E16474-455, display both types of echoes simultaneously, an overlapping whisper of spacetime and stardust. Then there's the wildcard, quantum spacetime foam. A controversial theory suggests that on microscopic scales, space isn't smooth but frothy, with tiny fluctuations that could subtly alter light's path. If neutron star echoes vary in ways neither relativity nor dust can explain, they might be hinting at this deeper layer of cosmic texture. Every delayed photon is a breadcrumb leading us closer to understanding how gravity, matter, and the vacuum itself behave when pushed to the breaking point, one echo at a time. Pulsars are often described as cosmic lighthouses spinning neutron stars that sweep beams of radiation across space with clockwork precision. But astronomers have stumbled upon a bizarre gap in the population of these celestial timekeepers. Between the rapid-fire millisecond pulsars spinning hundreds of times per second and the slower, elder statesmen ticking once every few seconds, there's a desert, a strange absence of pulsars with spin periods between 10 and 100 milliseconds. Where did all the middle-aged pulsars go? One explanation lies in the physics of the beams themselves. As pulsars age, their spin slows and their magnetic fields, which funnel radiation into those iconic lighthouse beams, gradually weaken. Over hundreds of thousands of years, this decaying magnetism might cause their beams to narrow, shrinking until they're too thin to sweep across Earth's line of sight. Imagine a lighthouse whose rotating lamp grows dimmer and more focused over time. Eventually, ships at sea would stop seeing its flashes entirely. The same could be happening with these midlife pulsars. They're still spinning, still beaming, but their signals have become so pinpoint that we're no longer in the path of their light. But not everyone's convinced that beam narrowing tells the full story. Some researchers suggest these pulsars might skip the middle-aged phase entirely thanks to an unexpected cosmic lifeline nearby companion stars. In binary systems, a neutron star can siphon gas from its partner, a process that not only re-energizes its spin but also recycles its magnetic field, effectively reset its aging clock. This could explain why we see so many millisecond pulsars spinning far faster than standard physics predicts. If recycling is common, it might mean that mid-speed pulsars are rare simply because they don't stay that way for long. Either they slow into obscurity or get a second wind and accelerate into the millisecond regime. Then there's the dark horse theory. The desert isn't real at all. Our telescopes might be missing these pulsars because their emission has shifted into a part of the spectrum we're not monitoring closely. Young, fast pulsars tend to shine brightly in radio waves, while older ones often fade, but some could transition to emitting more X-rays or gamma rays as they age, slipping through the cracks of traditional surveys. The discovery of a handful of hidden middle-aged pulsars in X-ray data, like the enigmatic PSRJ 0700-7158, lends weight to this idea. Perhaps the most tantalizing possibility is that some of these missing pulsars have transformed into something else entirely. The boundary between neutron stars and black holes is still poorly understood. Could a subset of mid-life pulsars cross some critical threshold of spin and density, quietly collapsing into black holes without the fireworks of a supernova? Or might they enter a phase where their magnetic fields become so tangled that their beams destabilize entirely, flickering out like a dying light bulb? Every undiscovered pulsar in this desert is a challenge to our models, forcing us to question whether we truly understand how these cosmic beacons live, age, and fade into the darkness. Deep in the constellation Sextans, a neutron star plays a cosmic game of peek-a-boo with astronomers switching personalities so dramatically it's earned the nickname PSR Jekyll and Hyde. One moment, it's a textbook radio pulsar, blasting out steady lighthouse-like beams of radio waves. The next, it transforms into an entirely different beast, an X-ray pulsar, glowing fiercely with high-energy radiation before fading back to radio silence. This celestial shape-shifter doesn't just challenge our classifications, it defies the very idea that neutron stars should behave predictably at all. What could drive such extreme metamorphosis? The leading suspect is a cosmic tug-of-war between the neutron star's magnetic field and the winds of its companion. Unlike solitary pulsars spinning quietly in isolation, Jekyll and Hyde orbits a sun-like star close enough to steal material from its outer layers. Normally, this stolen gas would funnel onto the neutron star's surface, heating up and emitting X-rays, the hallmark of an X-ray pulsar. But Jekyll and Hyde's magnetic field is unusually strong for this type of system, acting like a force field that can temporarily repel the incoming stellar wind. When the shield holds, the star reverts to its radio pulsar state, beaming cleanly through the repelled material. But when the companion's wind overwhelms the magnetic barrier, gas crashes through, igniting X-ray fury. Yet there's a twist that makes this system even stranger. The transitions aren't smooth or gradual, they're abrupt, flipping between states in as little as 10 days. That speed suggests something far more volatile than a simple balance between inflow and magnetic resistance. Some astronomers speculate the star's magnetic axis might physically shift during these transitions, like a wobbling top that occasionally tilts sideways. If true, this would cause the star's emission beams to suddenly point in new directions, explaining why we sometimes see radio pulses and other times detect only X-rays. Other theories point to instabilities in the companion star itself. Perhaps it sporadically belches denser winds that temporarily swamp the pulsar's defenses. The most tantalizing clue comes from the X-ray bursts themselves. Unlike steady accretion-powered pulsars, Jekyll and Hyde's X-ray mode flickers with erratic intensity, as if the star is struggling to digest its stolen meals. This could mean the magnetic field isn't just a static barrier but an active participant, reconfiguring itself in real time like a malfunctioning force field. Supporting this idea are observations of similar systems where magnetic reconnection events, sudden rearrangements of field lines, trigger violent X-ray flares. If Jekyll and Hyde's field is similarly dynamic, it might explain the star's identity crisis. But the biggest puzzle remains why we don't see more neutron stars behaving this way. Is Jekyll and Hyde a rare misfit, or are we just missing others like it because our telescopes aren't looking at the right times? Recent surveys have spotted a handful of potential mimics, pulsars that seem to vanish from radio wavelengths only to reappear months or years later. Could these also be shape-shifters hiding in plain sight? Every flip between Jekyll and Hyde's dual identities offers astrophysicists a chance to study neutron star magnetism in action, revealing how these cosmic chameleons dance on the edge of two very different stellar realities. Even the smoothest-looking neutron stars hide tiny imperfections, cosmic wrinkles so small they would barely register on a human scale, yet so dense they warp the fabric of spacetime itself. These deformations, nicknamed mountains, aren't towering peaks like Everest but microscopic bumps barely a few millimeters high. That might sound insignificant, but on an object with the mass of a sun squeezed into a 12-mile-wide sphere, even the tiniest irregularity generates mind-bending gravitational effects. If you could run your finger across the surface of a neutron star, those millimeter-high ridges would feel like climbing a mountain range made of pure neutronium, material so dense a single grain would weigh millions of tons. What creates these bizarre space-time wrinkles? One culprit is the neutron star's unimaginably strong magnetic field, which twists and stretches the star's crust like taffy. Picture a balloon covered in rubber bands. If some bands are tighter than others, the surface distorts unevenly. Similarly, magnetic stresses can push parts of the crust upward while depressing others, creating minuscule hills and valleys. Another factor might be starquakes, sudden fractures in the crust that leave behind scar-like ridges. And there's an even stranger possibility. Some mountains could be frozen relics from the star's violent birth, imprinted during the supernova collapse like fingerprints in cooling metal. The real puzzle is why we haven't definitively spotted these space-time warps yet. According to Einstein's theory, any asymmetrically shaped massive object, even one with millimeter-high mountains, should ripple the fabric of the universe with gravitational waves as it spins. These waves would carry energy away from the star, subtly slowing its rotation over time. Current gravitational wave detectors like LIGO and Virgo are exquisitely sensitive, but neutron star mountains might still be too faint to detect. The waves they produce would be 1,000 times weaker than those from colliding black holes, drowned out by the cosmic background noise of the universe. But there's hope on the horizon. Next-generation observatories like the planned Einstein telescope or space-based LISA could finally catch these whispers of distorted spacetime. Some theorists even suggest looking for indirect clues like unexpected slowdowns in pulsar spins that match the energy loss predicted by mountain-generated waves. The wild card, if mountains are rarer or smaller than models predict, it could mean neutron star crusts are far stronger than we thought, resisting deformation like cosmic diamond armor. The most tantalizing possibility is that these tiny imperfections aren't just surface features, they could be windows into the star's unfathomable interior. The way a mountain forms, shifts, or collapses might reveal whether the crust floats on a sea of superfluid neutrons, a quark-gluon plasma, or something even stranger. Every millimeter-high bump is a foothold for discovery, a clue to how matter behaves when crushed beyond recognition. And if we one day detect their gravitational echoes, it won't just solve a mystery, it'll prove that even the universe's most perfect spheres are rough around the edges. Some cosmic oddities don't just bend the rules, they rip them up entirely. Pulsar J1903+0327 is one such rebel, a pulsar locked in a gravitational dance so bizarre it makes astronomers question everything they know about stellar relationships. Unlike most binary neutron stars, which orbit in neat, circular paths with other compact objects like white dwarfs or fellow neutron stars, this misfit pulsar follows a wild, stretched-out ellipse around an utterly ordinary sun-like star. It's the cosmic equivalent of finding a cheetah yoked to a plow, two things that simply shouldn't coexist, let alone revolve around each other in such a lopsided embrace. So how did this mismatched pair end up together? Normally, pulsars with sun-like companions are expected to have circular orbits, the result of billions of years of gravitational interactions and tidal forces smoothing their path. Yet Pulsar J1903+0327's orbit is so elongated that at its closest approach, it swings nearly 3 times nearer to its star than at its farthest point. This kind of extreme eccentricity is usually seen in systems where both objects endured violent pasts, perhaps a supernova kick or a near collision with another star. But a sun-like star has no business surviving such chaos unscathed. Its calm, steady presence suggests it never experienced the stellar bar fights that typically warp orbits this drastically. One possible solution to this paradox involves an invisible third actor, a runaway star or black hole that once meddled in this system before vanishing into the galactic void. Picture this: long ago, the pulsar might have belonged to a tight binary with another massive star. When that star exploded, the newborn pulsar got a gravitational kick, sending it careening toward the sun-like star's vicinity. But instead of a clean capture, a third object, perhaps another star passing too close, could have yanked the pulsar into its current lopsided orbit before being flung away by the encounter. Gravitational sleuthing has indeed revealed hints of extra forces at play in this system, though no third body has been spotted yet. Another explanation dives into the pulsar's own history. Some theorists suggest it might be a recycled pulsar, one that was spun up by accreting material from a now-dead companion. If that original partner was vaporized in a cataclysmic event, the pulsar could have been left with enough momentum to carve out this strange orbit around the Sun-like star later on. The smoking gun, the pulsar spins an unusually brisk 465 times per second, a telltale sign of past feasting on stellar material. Yet the most tantalizing possibility is that we're witnessing a cosmic kidnapping. The Sun-like star might have once had its own binary companion, one that got ripped away during a close encounter with the pulsar's progenitor system, leaving the pulsar trapped in its place. Simulations show such gravitational heists can leave behind wonky orbits, though none quite as extreme as this. Every observation adds new wrinkles to the mystery, forcing astronomers to ask, is this pulsar a freak accident or a sign that our understanding of stellar dynamics is missing a crucial chapter? Until we track down that hypothetical third object or uncover more systems like it, this gravitational outlaw will keep defying the odds, one elliptical orbit at a time. Some neutron stars refuse to play by the rules. They glow fiercely in gamma rays while remaining stubbornly silent in every other wavelength. HES J1731-347 is one of these enigmatic objects, beaming out high-energy radiation while showing no trace of the radio or X-ray pulses that typically betray a pulsar's presence. It's like finding a roaring bonfire that somehow casts no light, only heat. What could possibly explain such a cosmic contradiction? One possibility is that we're dealing with a magnetar in camouflage. These ultramagnetic neutron stars are notorious for unpredictable outbursts, often flaring in gamma rays while staying quiet in other parts of the spectrum. But HES J1731-347 doesn't behave like a typical magnetar either. It lacks the violent X-ray eruptions and rapid spin-down rates that usually give them away. Instead, it emits a steady stream of gamma rays with eerie consistency, more like a lighthouse stuck on high beam than a temperamental cosmic flare. Could this be a magnetar in an unusually calm phase, or is it something even stranger, a neutron star with magnetic fields so twisted they only channel energy into gamma rays? Geometry might also be the culprit. Pulsars emit radiation in narrow beams from their magnetic poles, meaning we only detect them if those beams happen to sweep across Earth. If HES J1731-347's gamma-ray beam is angled sharply away from us while its radio and X-ray emissions are even more narrowly focused, we might be catching just a sliver of its full output. Picture standing next to a spotlight. If it's pointed straight up, you'd only see scattered light, not the central beam. Similarly, this neutron star could be shouting in gamma rays while whispering in other wavelengths, its full brilliance hidden by the cosmic equivalent of a tilted lampshade. Then there's the wildcard explanation, an entirely new class of neutron star. Some theorists speculate that certain exotic configurations of matter, like quark stars or hybrid objects with cores of free-floating quarks, could produce unusual emission patterns. If HES J1731-347's core is a seething mix of neutrons and quark gluon plasma, its energy release mechanisms might differ radically from ordinary pulsars, favoring gamma rays over other forms of radiation. Supporting this idea are observations of other gamma-ray-only sources like the mysterious Geminga, which also defies traditional classification. The most tantalizing clue lies in the star's surroundings. HES J1731-347 sits inside a supernova remnant, cocooned in debris that could be absorbing or scattering its lower energy emissions. If the remnant's gas is particularly dense, it might act like a cosmic fog, muffling radio and X-ray pulses while allowing higher energy gamma rays to punch through. Alternatively, interactions between the neutron star's magnetic field and this surrounding material could generate gamma rays directly, like a natural particle accelerator. Every silent neutron star is a challenge to our assumptions, forcing us to wonder how many more might be lurking in plain sight, their true nature masked by geometry, environment, or physics we've yet to uncover. Until we catch one of these gamma-ray phantoms in a moment of transformation, or develop telescopes sensitive enough to probe their hidden depths, they'll remain cosmic riddles wrapped in enigmas, whispering their secrets in a language we're still learning to decode. Most neutron stars scream their presence across the cosmos with searing X-rays or rhythmic radio pulses, but RxJ1 856.5-3754 refuses to follow the script. This cosmic loner, drifting through space some 400 light-years away, glows with an eerie blue tint in visible light while emitting X-rays so faint they barely register. At first glance, that wouldn't be unusual. Older neutron stars cool over time. But here's the catch. This object's X-ray profile suggests it's only about 12 miles across, nearly 20% smaller than any known neutron star. In the world of ultra-dense stellar remnants, that's like finding a bowling ball that somehow weighs less than a ping-pong ball. One radical explanation has physicists buzzing. What if RxJ1 856.5-3754 isn't a neutron star at all, but something far stranger, a quark star? Under normal conditions, quarks, the fundamental building blocks of protons and neutrons, are forever confined inside larger particles, but crush matter hard enough, as in a neutron star's core, and those quarks might break free, forming an exotic soup where up, down, and strange quarks mingle freely. A pure quark star wouldn't have a crust of neutrons at all. It would be a uniform sphere of quark matter from surface to core, potentially explaining this object's unusually compact size. The star's peculiar blue glow could then be the thermal fingerprint of this exotic state, cooling differently than neutron-rich surfaces. But before we rewrite the textbooks, there's a less flashy possibility: cosmic camouflage. Neutron stars are thought to develop thin atmospheres, either from residual heat or accumulated interstellar gas. If RxJ1 856.5-3754 has an unusually thick hydrogen blanket that could absorb and reprocess its X-rays, making the star appear smaller and cooler than it really is. Picture wrapping a white-hot iron ball in a layer of fog. The glow would soften and the apparent size would shrink. Some models suggest this atmosphere might even form a superfluid film, distorting our measurements further. The real intrigue lies in the star's motion. Unlike most isolated neutron stars, which trace graceful arcs across the sky, this object barrels through space at nearly 150 kilometers per second, trailing a faint bow shock of heated gas. That speed hints at a violent birth, perhaps a supernova explosion so asymmetric it kicked the newborn star like a cosmic soccer ball. If true, the blast might have also stripped away much of the star's original outer layers, leaving behind an exposed quark core or an unusually thin atmosphere. Supporting this, Hubble Space Telescope observations reveal a slight excess of ultraviolet light around the star, possibly the ghostly echo of gas torn away during its chaotic infancy. The most tantalizing clue comes from what we don't see. Unlike pulsars, RxJ1 856.5-3754 shows no magnetic activity, no bursts, no variability, just a steady, cool blue whisper. If it were a quark star, its uniform structure might suppress magnetic fields entirely, explaining the silence. Alternatively, if it's an ultra-dense neutron star with a photon-cooling surface, its emissions could be channeled into invisible wavelengths slipping past our telescopes. For now, this cosmic oddball remains an enigma. Is it the first confirmed quark star, a neutron star in an unprecedented state, or something entirely new? Every flicker of its blue light carries a challenge to our understanding of matter itself, proof that even in the coldest corners of space, the universe still has surprises up its sleeve. Even the most reliable cosmic clocks sometimes skip a beat. Across the galaxy, astronomers have spotted pulsars that flicker unpredictably, not just dimming slightly, but vanishing entirely for minutes, hours, or even months before roaring back to life as if nothing happened. These sudden blackouts, known as nulling, defy the very definition of pulsars as steady celestial metronomes. Take PSRB 1931+24, for example. This otherwise ordinary pulsar once went silent for 40 days without warning, leaving astronomers staring at empty radiostatic before it abruptly resumed its rhythmic pulses like a cosmic game of peek-a-boo. So what cuts the power to these spinning lighthouses? One leading theory points to turbulence in their magnetospheres, the invisible cages of magnetic fields and charged particles surrounding the star. Normally, these magnetospheres act like cosmic particle accelerators, funneling radiation into tight beams from the magnetic poles. But if the field lines momentarily tangle or collapse, the pulsar's engine could sputter, choking off the beams entirely. Imagine a garden hose with a kink. Water flows smoothly until a twist interrupts the stream, then resumes just as suddenly when released. Observations of nulling pulsars like PSRJ 1502-5755 support this idea, showing telltale magnetic hiccups preceding each shutdown. Yet there's a competing explanation: cosmic eclipses. Some pulsars, especially those with companion stars, might be shrouded in thick clouds of plasma superheated gas stripped from their stellar partners. As these clouds drift across our line of sight, they could act like celestial blinds, temporarily blocking the pulsar's signal. The Black Widow pulsar offers a clue here. Its radio pulses often fade when its evaporating companion is closest, as if the star's dying gasps are smothering the beam. But this can't explain nulling in isolated pulsars, leaving astronomers to wonder if some generate their own obstructive plasma. The wild card is stranger still. Some nulling pulsars, like PSRJ 1832+0029, don't just go dark. They shift frequencies before vanishing, as if their beams are being refocused into wavelengths we can't detect. This suggests the pulsar isn't truly turning off, but rather redirecting its energy, like a lighthouse whose rotating lens suddenly jams, pointing its beam into empty ocean instead of toward shore. Supporting this, X-ray telescopes occasionally catch nulling pulsars still shining brightly in high-energy light while their radio voices go silent. Perhaps the most unsettling possibility is that these nulls are symptoms of a deeper transformation. Some theorists speculate that pulsars might periodically enter sleep modes, where their internal dynamo, the engine powering their magnetic fields, briefly stalls before rebooting. If true, each null could represent a star on the brink of permanent shutdown, offering us fleeting glimpses into the final chapters of a pulsar's life. Every silent moment is a cosmic puzzle, challenging us to decipher whether we're witnessing a glitch, an eclipse, or the universe's most dramatic game of hide and seek. Most stars live and die in relative stillness, but neutron stars, some blast into space at speeds that defy reason, rocketing through the galaxy at over 1,000 kilometers per second. That's fast enough to cross the continental United States in less than 5 seconds, or journey from Earth to the Moon in under 7 minutes. The real mystery isn't just their speed, but how these cosmic cannonballs get launched in the first place. What force in nature could possibly hulk a stellar corpse heavier than the Sun, faster than a hypersonic bullet? The prime suspect lies in the chaos of their birth. When a massive star explodes as a supernova, the collapse isn't always neat and symmetrical. Picture a balloon popping. If one side bursts first, the recoil sends the rest flying off kilter. Similarly, if the supernova's shockwave ripples outward unevenly, the newborn neutron star could get a staggering gravitational kick from the blast's lopsided fury. This might explain stars like the guitar pulsar, streaking through space so fast it's carving a sonic boom-shaped wake in interstellar gas. Simulations show these kicks could reach speeds up to 500 kilometers per second, but that still leaves the true speed demons unexplained. That's where magnetism comes in. Neutron stars aren't just dense, they're magnetized, with fields strong enough to warp the fabric of space itself. Some theorists argue that if these fields are tangled like spaghetti during the supernova, their violent snapping into alignment could act like a cosmic slingshot. Imagine twisting a rubber band tighter and tighter until it finally whips free. That's the kind of recoil that might launch a neutron star to hypervelocity speeds. Supporting this, astronomers have noticed that the fastest-moving pulsars often have unusually strong magnetic fields, as if their acceleration left an electromagnetic fingerprint. Yet there's a third, wilder possibility: binary breakup. Before their explosive deaths, many massive stars orbit partners. If one star goes supernova and suddenly loses most of its mass, the surviving neutron star could get flung away by the remaining gravitational imbalance, like a hammer thrower letting go mid-spin. The runaway pulsar PSRJ 075 1+1 might be a case of this, its trajectory hinting at a violent divorce from a now-vanished companion. The stakes go beyond stellar forensics. If we can pin down the kick mechanism, it could rewrite how we map the galaxy's history. Neutron stars born in tight star clusters, for example, should get ejected at predictable angles, yet many are found outside these regions, suggesting even earlier kicks than we thought. Others, like the infamous Black Widow pulsar, zoom through space while vaporizing a companion, proving some kicks happen after the star's rebirth. Every hypervelocity neutron star is a fossil of its explosion, a cosmic crime scene where the laws of physics left their fingerprints. Decoding their paths isn't just about speed, it's about reconstructing the final, violent moments of stellar death itself. And with each new discovery, we're one step closer to understanding how the universe plays favorites, giving some stars a gentler exit while others get flung into the void like interstellar outlaws. Deep within the crushing heart of a neutron star, another invisible mystery might be lurking, one that could rewrite our understanding of the universe's most elusive substance, dark matter. Picture this: what if these cosmic pressure cookers aren't just laboratories for extreme matter, but also traps for shadowy particles that otherwise slip through our detectors unnoticed? The idea isn't as far-fetched as it sounds. Neutron stars' insane gravity and density make them perfect dark matter sinks. Even a whisper of interaction between dark matter particles and neutronium could leave fingerprints: abnormal heat where none should exist, or cooling rates that defy every model. Take the case of the neutron star in the Cassiopeia, a supernova remnant. This stellar corpse is cooling way faster than theories predict, as if some unseen energy leak were siphoning heat from its core. Normally, neutron stars chill by emitting neutrinos, ghostly particles that carry energy into space. But Cassiopeia A's temperature drop is so abrupt it's like watching an oven switch off mid-bake. One provocative explanation: dark matter particles accumulated over millennia might be colliding and annihilating inside the star, injecting extra heat that alters its cooling trajectory. It's a cosmic balancing act. The same reactions that could keep the core artificially warm might also accelerate neutrino emission, creating a paradoxical cooling spike. But how would dark matter even get there? Most theories assume these particles barely interact with normal matter, drifting through planets and stars like ghosts. Yet neutron stars are different. Their gravitational pull is so intense that passing dark matter particles could lose energy and become trapped like flies in cosmic amber. Over billions of years, enough could accumulate to form a swirling reservoir in the star's core. If those particles occasionally collide, releasing energy via annihilation, they'd act like invisible furnaces, subtly reheating the neutron star from within. The smoking gun might lie in outliers like the Magnificent Seven, isolated neutron stars that should be freezing cold, yet somehow radiate faint excess warmth. If dark matter densities vary across the galaxy, stars in regions thick with it, like the Milky Way's center, might show anomalously high temperatures compared to those in dark matter deserts. Intriguingly, the few neutron stars we've spotted near the galactic core do seem to run hotter than expected, though confirming a dark matter link remains tricky. Yet skeptics counter with alternative explanations. Maybe fast-cooling neutron stars like Cassiopeia simply have superfluid cores that enhance neutrino emission, no dark matter required. Or perhaps their crusts conduct heat differently due to exotic nuclear structures. The wild card, some theories suggest dark matter could trigger phase transitions inside neutron stars, converting ordinary neutrons into hyperons or quark matter processes that would also tweak cooling rates. Untangling these possibilities isn't just academic. It could give us our first tangible glimpse into dark matter's properties. Imagine if neutron stars, those brilliant beacons of extreme physics, are also silent dark matter detectors. Their temperatures encoding secrets about particles we've hunted for decades. Every anomalous cooling curve, every unexplained heat spike, might be a message from the universe's shadow realm waiting for us to crack the code. At the end of time, when the last stars flicker out and the universe grows cold, what becomes of neutron stars, these indestructible remnants forged in stellar explosions? Their fate is more complex than mere fading or collapse, entangled with the deepest laws governing matter, energy, and the very arrow of time itself. Consider the simplest possibility, cooling into cosmic ghosts. Over trillions of years, even the searing heat trapped in a neutron star's core will slowly leak away, carried off by neutrinos and feeble thermal radiation. The surface, once glowing at 1,000,000 degrees, would cool to near absolute zero, leaving behind a pitch-black sphere, a black dwarf, made not of carbon like its white dwarf cousins, but of degenerate neutrons. Yet this tranquil fade out isn't guaranteed. Quantum mechanics whispers another possibility: proton decay. If protons, the building blocks of neutronium, aren't truly stable but instead disintegrate over unimaginable timescales, the star's very structure could unravel. Picture a mountain of sand where each grain vanishes one by one. Over enough eons, the entire edifice would crumble into a whisper of radiation, leaving no trace behind. But entropy isn't the only threat. Some neutron stars might meet a far more dramatic end. If they accrete even a tiny bit more mass, whether from interstellar gas or a hapless planet, their already overburdened cores could cross the threshold of stability, collapsing into black holes without a whisper. Simulations suggest this final plunge might not be instantaneous. For a fleeting moment, the star could exist as a hybrid, a quark matter core wrapped in a neutron shell, teetering on the edge of oblivion before vanishing behind an event horizon. The kicker: this process could still be happening today. Ancient neutron stars drifting through dense molecular clouds or cannibalizing dark matter might be silently tipping the scales right now, vanishing one by one like sinking stones in a cosmic pond. Then there's the wild card: transformation. In the universe's dying epochs, as temperatures plummet and energies fade, conditions might become ripe for neutron stars to undergo a phase transition, not into nothingness but into something even stranger. Theoretical models suggest that under extreme cold and pressure, the neutrons in their cores could melt into a sea of free-floating quarks, creating stable quark stars. These would be the ultimate end state of matter, impervious to further decay, glowing faintly with the residual heat of a universe that's long since forgotten the fire of stars. The cruel irony: we may never witness these endings firsthand. the timescales involved stretch far beyond the lifespan of galaxies, but neutron stars offer clues in the present. By studying how their spins slow, how their surfaces cool, or how their masses cluster near the theoretical limit, we're glimpsing the blueprint of their ultimate destinies. Each pulsar's steady tick is not just a timekeeper's beat, but a countdown to the universe's final act, a reminder that even the mightiest objects in the cosmos are bound by time's inexorable flow. Whether they fade, collapse, or transform, their fates are woven into the same tapestry that dictates the end of all things, the slow, inevitable victory of entropy over energy, of silence over light. From their violent births in supernova explosions to their silent, dark fates trillions of years in the future, neutron stars and pulsars are cosmic laboratories where the laws of physics get pushed to the breaking point. We've explored 25 of their deepest mysteries, how they defy density limits with quark cores, flicker like broken lighthouses with nulling pulsars, and even vanish entirely into the missing pulsar problem. We've seen them shape-shift between radio silence and X-ray fury, launch themselves across galaxies at hypersonic speeds, and possibly even trap dark matter in their crushing embrace. Each puzzle forces us to rewrite the rules. Why do some neutron stars suddenly break instead of accelerate? How do planets survive their star's explosive death? And what happens when a magnetar's unimaginable magnetic field snaps like a rubber band? These aren't just curiosities, they're frontiers. Every glitch, every burst, every gravitational ripple from these stars is a challenge to our understanding of matter, energy, and space-time itself. They ask us questions we're only beginning to frame. Is there a point where neutrons dissolve into something stranger? Can a star be so dense it becomes a gateway to new physics? The answers could redefine everything from quantum theory to cosmology. Now it's your turn. Which mystery pulled you in the most? The enigma of pulsar planets, the riddle of anti-glitches, or the haunting silence of missing stellar corpses? Drop your thoughts in the comments. Let's geek out over the universe's most extreme objects together. And if you're hungry for more deep dives into cosmic weirdness, hit subscribe. The universe is full of puzzles, and we're just getting started.